Hi, welcome to the second mini lecture on Laplace transforms. The first mini lecture we looked at the definition, some of the conditions, and we started to derive Laplace transforms of some useful expressions. We're going to continue with that this time. We're going to work through a few expressions which are common and useful for control problems. Then the next mini lecture after this, we're going to look at how to manipulate the Laplace transform functions so that we can turn it into a form that we can easily find the inverse functions from tables. Translated functions. What does that mean? Well, this is a common occurrence. We've got some function, we've called it f of t. It starts at t equals 0, it goes up, it wiggles around a bit, so that could be anything. A lot of systems will introduce a lag or something like that into a response. So now at t equals 0, nothing happens. After some delay, t0, there's our function again. The function hasn't changed, just moved in time, it's shifted in time. It's called a delayed function when it's going to happen later, and it's called an advanced function when it's going to happen sooner. The function hasn't changed, and so we can keep f as it was. What we need to do is to recognize that the time has shifted. So we can replace t with t minus t0 for the delayed case. So that means now when t is equal to t0, this will be f of 0. So at this point here, where t equals t0, it'll be f of 0, which is the same as this point here, f of 0. So we've taken the same function, we've shifted it. Here it's delayed, here it's advanced. What happens when we try and find the Laplace transform of that? Okay, so there's our function we've put in. Now we need to try and manipulate that. So the first thing we do is we want to get all of our terms into t minus t0s, because that will match what our function looks like. So here we've got e minus st. Well, we can multiply by e minus s minus t, that's the same as e st, and multiply again by e minus st0, sorry, that's a t0. And so the combined effect of multiplying by e to the minus st0 and e to the st0 is equal to 1 unity. We've just introduced it so that we can then put this into this form t minus t0. That's good. The differential term we've written again as t dt minus t0. Well, we can do that because dt is equal to dt minus t0. t0 is a constant, so you take the differential of that and it's equal to dt. Okay, so now we've done that, we can make a substitution. So we say t minus t0 equals tau, and we can rewrite our expression. So now the expression looks like e to the minus st0. We've got our integral from minus t0 to infinity because the limit has changed with our substitution, and this now looks like f of tau e to the minus s tau d tau. So this is looking a lot like a Laplace transform function. We need to change the limits of the integral. We've changed it to 0 to infinity rather than minus t naught to infinity. Is that okay? Well, for our delayed function, that's not a problem because everything's equal to 0 anyway when t is negative. So these two things are the same. That's great. That's now given us an expression for our Laplace transform. This is the Laplace transform of f of tau, so we call that f dash s, f bar s, and this is representing our time shift. So a time shift can be represented simply by taking the Laplace transform of the function without the time shift and multiplying it by e to the minus s t0, where t0 is the delayed time shift. So we can see how a translated function, again, it's easily accommodated within the mathematics of Laplace transforms. We'll just look at an example of how this can occur. Let's take a pipe with a flow down it. This is a pipe which is plug flow, so material comes in and it just flows as a plug and it comes out the other end. let's look at the temperature. T in is the function representing temperature coming in, and the exit T out is the temperature coming out. And Td, that's the time it takes for the fluid to flow the length of the pipe. Okay, so the Laplace transform of T in is going to be T bar in of S. And we'd like to know the Laplace transform of what's coming out. So the Laplace transform of T out, so that's T out bar S, is going to be equal to the Laplace transform of T in with the delayed time shift. Nothing's changing as it flows down the pipe, it just takes a time Td to get from one end to the other. So whatever goes in is going to come out after a time delay of Td. So that can then be written very easily as e to the minus std multiplied by the Laplace transform of the input T in bar. So that's how that works. It's nice and simple, and again it incorporates another aspect of process control in a simple mathematical framework. Here we go, another one, the unit pulse function. What does that mean? This is the case where something comes on and then it goes off. At time 0 our function goes up to a value of 1 divided by a. It stays constant at 1 divided by a until time t equals a, and then it drops down again to 0 and is constant at 0. It's called a unit pulse because the area of the pulse, the integrated area here, is equal to 1. So the width of the pulse is a, the height of the pulse is 1 over a, multiply them together, area is equal to 1. So again, this is going to represent common occurrences on a plant where something happens for a period of time and it stops happening. And again, we've got discontinuities at t equals 0 and a, so we need to recognise that as we write the function. So the unit impulse, it's commonly written as delta a t, so it's a unit impulse. And equals 0 when t is less than 0, 1 over a when t is between 0 and a, and then it goes back to 0 when t is above a. Again, on the boundaries, t equals 0, t equals a, it's undefined. So how can we find the Laplace transform of that? Well, now we can take advantage of the linearity of the transform. So we can say that our unit function is simply the addition of two other functions. It's the addition of a step increase. Apologies, it's the subtraction. We have a step increase and then we subtract from it another step increase which is delayed in time. So we have this one, we subtract that one from it. That's going to give a function which comes along, goes up at t0, progresses constantly, and then steps down again at t equals a. We can do it this way because we know these things already. We know this function, and we know how to represent a delayed function, and we know that we can add and subtract Laplace transforms. So just write out what these are specifically. 0 for t is less than 0, 1 over a for t is greater than 0. This is 0 until t is greater than a, and then it's equal to 1 over a. And that can be written as a time delayed function. So it's the same as f1, except it's got the delay of a. So our unit step function, our unit pulse function of duration a, is equal to f1 of t minus f2 of t, and we saw that f2 can be represented as f1 of t minus a to represent the delay. So that's the Laplace transform we want to find, and here we take advantage of the linear properties that we can separate out this subtraction so that we have the Laplace transform of the first function subtracted by the Laplace transform of the second function. And then we can take advantage of what we know about a delayed function. We can represent that delay as e to the minus sa, and now this is just the Laplace transform of f1, and that's the Laplace transform of f1. That's so nice and simple. We substitute in the result that we've derived before for the step increase. So there it is there, and there it is there again. And then we rearrange that to get this expression. So now we have the Laplace transform for a unit step pulse of duration a. It's 1 over a, 1 minus e to the minus SA divided by S. So next we look at a special case called the unit impulse function. So the unit step function went up for a period of time and then went down again. Well, let's imagine that the period of time shrinks, gets smaller and smaller until it's infinitesimally small. Now we've got a function which is 0. At t equals 0, it shoots up infinitely high, shoots back down again, and then continues at 0. We call this the unit impulse. It's also called the Dirac function and has the normal symbol delta t. So even though it's 0 over everything apart from t equals 0, it is still a thing. So the area remains the same as the unit pulse function. And we're considering the limit as a tends to 0 of a divided by a, and that is equal to 1. So this function has an area of 1, even though it is only there for an infinitesimally small time. And the consequence of that is that when t equals 0, this value, this function f of t, is infinitely high, so it doesn't have a value for its height. But it's a useful function. It represents an approximation of what can happen in real life, where you have a very sudden, very short duration event. So if you integrate from minus to infinity of the unit impulse function, its area is equal to 1. Okay, we want to find Laplace transform of that. No problem. So let's find the Laplace transform for the unit pulse function, but let's do that when we're finding the limit as a tends to 0. That's the Laplace transform definition here, so we've written it into the integral, and then we will work through that. Okay, here we go. So we've written it in. There's our unit impulse function, and what we've done is we've taken the limit outside the integral. A is a constant, so we can do that, and we can integrate the unit impulse function so we can use the result that we know for the Laplace transform of the unit pulse function and substitute that in here. So that's the result we found for the previous example for the unit pulse function, and then we just find the Laplace transform for the impulse function by taking the limit as a goes to 0. We have a problem there because we've got a 0 on the bottom, so we use L'Hopital's rule and we take the differential of the top and the differential of the bottom, so we're differentiating with respect to a. So when we differentiate as, it becomes s, and when we differentiate 1 minus e to the minus sa, it becomes s e to the minus sa. Now we can put in our limit as a tends to 0, e to the 0 is equal to 1, s divided by s is equal to 1. So we've proven that the Laplace transform of the unit impulse function is equal to 1. Something to take note of. We've seen that functions that are translated in time, they have an exponential term in their Laplace transform. So they've got a term like that, e to the minus t0s. So something that's translated has that, but everything else we've seen is of this form. The Laplace transform of all the other functions, it's a fraction of one polynomial of s divided by another polynomial of s. And so in the most general case, you can say q1 is a polynomial of s, so it's s to the power m multiplied by some coefficient, and so on until we get to just s to the power 0. And likewise on the bottom. So we're taking note of that. That's going to be a really useful result, is that the Laplace transforms all behave in this way, that we can accumulate the functions and combine them together, and it will give us a simple fraction of one polynomial of s divided by another polynomial of s. A couple more things we want to do. We said we want to use Laplace transforms to solve differential equations, so we need to look at the case for derivatives and integrals. Now we're taking the Laplace transform of a derivative of f with respect to t. Obviously we input that into our definition for the Laplace transform, and we can start to work through what this will look like. We're going to need to use integration by parts to get the separation of the two terms, and that works okay. So here we have e to the minus st times f of t, so we put in our limits. When t is infinity, this term will be 0. When t is 0, this term would be 1, and this would be equal to f of 0. So we have minus f of 0 there. Here we are with our second term. We've taken s outside. Now we've got the integral of f of t e to the minus st dt, and we recognise this is the same as the Laplace transform of the function ft. So we can rewrite that as simply the derivative, the Laplace transform of the derivative is equal to s times the Laplace transform of the function minus f of 0. That's really nice and simple, and that simplicity extends across high order differentiations, so d2 f by dt squared. Now we've got s squared multiplied by the Laplace transform of f minus s f of naught minus f dash of naught. So that means the first derivative at value 0. So we've spotted a pattern here, and this pattern it continues as the order of the integration increases. It's the same pattern, so for whatever differential you have, you can use the same pattern, but it's s to the n multiplied by the Laplace transform of the function, and then it's minus all of these terms at time, for the function at time 0, s n to the minus 1, s n to the minus 2 times the first derivative, s n to the minus 2, f n to the minus 1. So you can see the pattern there. So for an nth order derivative, we need n initial conditions. We have f naught, f dash naught, f double dash naught, and so on until we have fn minus 1 of naught. So we have all these terms that we need to have a value for. That makes sense when you're solving differential equations. You know that you need to have initial conditions or boundary conditions to solve your equation. So what we've seen again is that very nicely, even when we have differential terms in our problem, when we take Laplace transforms, we end up with this same sort of equation. We end up with polynomials of s. So all of our Laplace transforms, apart from the time shift, are of the same form, which we can easily manipulate when we combine them together. Let's look at integrals. Here we go. Now we've put the integral into the function for the Laplace transform. Now we need to do integration by parts again. Here I've shown the two parts, u and v, which gives du and dv, and you can look for yourself to work out that when we work through our integration by parts, that's how we're writing it, minus 1 over s of integral of v du, using these definitions of v and du. We can now put in our terms, vu minus u dv, substitute in for u and v across that. So v is equal to the integral 0 to t ft dt, that's here. U is equal to e to the minus st, there it is, e to the minus st. So we look at that term from limit 0 to infinity. Now we've got our minus 1 over s multiplied by minus 1, so it's positive 1 over s, integral of u dv, so u is equal to e to the minus st, e to the minus st, and dv is equal to ft dt, ft dt. And then we recognise that this is simply the Laplace transform of ft. So we can write that in and we can look at our limits here. Our limit when t is infinity, we've got an e to the minus t term here, so that's 0. Our limit when t is 0, that term is equal to 1, but here we're integrating from 0 to 0, and so that term is going to be 0 as well because that integral is 0. So that 0 minus 0 disappears, and we're left with 1 over s multiplied by the Laplace transform of our function. So again, we've got a very nice and simple expression in the Laplace transform of our integral term, and we can use that to represent integration in the Laplace transform space. Okay, our last slide here is to look at two theorems. The final value theorem. So if you have a function in time and we're looking as t increases, what will happen in the limit to our Laplace transform? So the theorem is that if you're looking at the limit of f of t as t goes to infinity, that's the same as looking at the limit of s of the Laplace transform as s goes to 0. And of course we can prove this. We start by writing out again here the Laplace transform for a differentiation, and we take the limits of each side of this. The limit as s tends to 0. We've applied the same limit to both sides, and so here's our limit s tends to 0 of that term. This is integrating with respect to t, so we can bring s inside. So we've taken the limit inside our integration here. So the limit as s tends to 0 of this term multiplied by the limit is equal to the limit of s tends to 0 of this term. Okay, what happens? Okay, well, df by dt, that stays here. But now we've got the limit as s tends to 0 of e to the minus st, that's equal to 1. As s becomes 0, that will be equal to 1. So that term reduces to this. And here we have separated these two parts, taking advantage of the linearity of the Laplace transform. The limit as s tends to 0 of the first part minus the limit as s tends to 0 of f0, and that will be equal to f0 since it's not a function of s. And so we've written out our theorem at the end. Similarly, for an initial value theorem, we see that the limit as ft as t goes to 0 is equal to the limit of s times the Laplace transform of f's as s tends to infinity. Okay, that's that finished. We've now finished all of the revision of Laplace transforms, of what they mean, and all of the examples we're going to look at. So we know how to find Laplace transforms now, we know a few rules about how to manipulate them, and we've seen the Laplace transforms of a number of really common and useful functions that are relevant to control. The next mini lecture is going to look at how to manipulate Laplace transforms into convenient forms so that we can interpret what they mean, and we can then use tables to find inverse Laplace transforms.